Hello students, welcome to this lecture, One Real Numbers. So in today's lecture, we will first recall some definition of like rational number, irrational number, and also we recall how can we locate irrational number on the number line. Okay, then we'll discuss an important theorems that actually based one fundamental theorem of arithmetic. Okay, and then we'll prove how to show root 2, root 3, root 4 are irrational number. Okay, so let's get started. So first question, what are irrational number? So student, you have studied in your class 9 first chapters number systems. There you have studied actually what are natural numbers, what are integers, what are rational numbers, and what are irrational numbers. Okay, so there you have studied actually natural number, actually the set of these numbers 1, 2, 3, 4, 5 and dot dot dot. This number actually set of natural numbers. Okay, so we denote set of natural numbers is by n. And we also studied what are integers. So set of integers basically is equal to set of dot 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 -3 -2 -1 0 1 2 3 dot dot dot. Okay, and whole numbers basically including 0 with natural number is called whole numbers. Set of whole numbers is denoted by w, and this is equal to 0 1 2 3 4 and 5 and dot dot dot. Okay, so now if we take if we take whole numbers and their negatives, okay, the negatives, then this will together will make integers, set of integers. Okay, and that is denoted by z, and set of integers z is equal to set dot 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 -3 -2 -1 0 1 2 3 4 dot dot dot. Okay, and then we have studied rational numbers. So rational number is basically is denoted by q, set of rational number denoted by q. So this is basically equal to set p over q such that p q from integers and q not equal to 0. Okay, so rational number basically are those numbers that can be expressed as a fraction. Okay, like p over q, where p q from integers and q not equal to 0. Okay, so now our question, what are irrational number? Okay, so irrational number basically are irrational number are numbers that cannot be expressed as a fraction a over b. Okay, where a and b are integers and b not equal to 0. Okay, so they are decimal expansion. If we define irrational number in terms of decimal expansion, so how can we define? So first we can define rational number by decimal expansion. Okay, so student, if you know, there are some types of decimal expansions like terminating decimal expansions, non-terminating repeating decimal expansions, and non-terminating non-repeating decimal expansions. Okay, so you know, rational number, the decimal expansion of a rational number is either terminating decimal expansions or non-terminating and repeating decimal expansions. Okay, so for example, you can take this number 1 by 3. So if we take suppose 1 by 2, so 1 by 2, so this number can be expressed as a p over q as a fraction. Okay, where the denominator 2 is not equal to 0. So this number is a rational number. Okay, so the decimal expansion of 1 by 2, what is decimal expansion of 1 by 2? That is equal to 0.5. Okay, so the decimal expansion of 1 by 2 basically is equal to 0.5. So here after decimal point, the digit is 5, and after decimal point the digit end with digit 5. Okay, so this decimal expansion basically terminating decimal expansion. Okay, so in terms of decimal expansion, this number actually is a terminating decimal expansion, so this number is a rational number. Okay, but if we take 1 by 3, so 1 by 3, this also is of the form a over b, where a b from integers and b not equal to 0. Okay, so 1 by 3 is a rational number. So now if we look at its decimal expansion, so the decimal expansion of 1 by 3 is basically equal to 0.333 dot dot dot. Okay, so this decimal expansion is basically non-terminating, and here after decimal point 3, this digit 3 repeating, okay, until infinity. Okay, till infinity. So 0.333 dot dot dot. This number is a rational number. Okay, since the decimal expansion of 1 by 3, that is 0.333, is a non-terminating and repeating decimal expansions. Okay, so for rational number there are two types of decimal expansion: terminating and non-terminating, non-repeating. Okay, so for a rational number, the decimal expansion of a rational number is either terminating decimal expansion or non-terminating and repeating decimal expansions. But in the case of irrational number, so in the case of irrational number, their decimal expansion is non-terminating and non-repeating decimal expansion. Okay, for example, you can take root over 2. So root over 2, the decimal expansion of root over 2, that is basically equal to 1.414 and dot dot dot. Okay, so this decimal expansion is a non-terminating, non-repeating decimal expansion. Okay, so root 2 is an irrational number. Okay, for root 3, root 3, pi and e, these type of numbers are actually irrational numbers. Okay, so here we defined irrational numbers. So irrational numbers are basically numbers that cannot be expressed as a fraction a over b, where a and b are integers and b not equal to 0. Okay, and their decimal expansion are non-terminating and non-repeating decimal expansions. Okay, and there are some examples of irrational number like root 2, root 3, pi, e, etc. Okay, now let us move to next topic: existence of irrational number. So actually, how we feel existence of irrational number. So one of the key realization that there are numbers that cannot be neatly classified as a fractions. Okay, so like root 2, the length of diagonal of a square with side 1. So this realizes that led to understand that irrational number fill in the gaps between rational number on the number line. Okay, so root 2, this is basically actually discovered Pythagoras. Pythagoras discovered root 2 is an irrational numbers. Okay, so he basically worked with this right angle triangle. The side of this is 1 unit and this is 1 unit, and he discovered Pythagoras theorem. Okay, so Pythagoras theorem actually stated to us the base of a rectangle square, area of the face of this base square plus height square, this is equal to hypotenuse square. Okay, so for this right angle triangle, the hypotenuse is basically root 2. Okay, so when he worked with this right angle triangle, he got root 2, this type of numbers. Okay, and he discovered root 2 is an irrational numbers. Okay, so this realization that led to understand that irrational number fill in the gaps between rational number on the number line. So student, we have studied in our class 9. Okay, there actually we have studied the representation of rational number and irrational numbers. Okay, so when we have studied representation of rational number on the number line, that case we get some gaps between two rational number. Okay, so between two rational number, actually we get some gaps. Okay, and here after coming irrational number fill in the gaps between between rational number on the number line. Okay, so student, you have studied how to represent rational number and irrational number on the number line. Okay, so suppose you have this number line. Okay, so here first we mark 0 as a point. Okay, and here in the right hand side of the 0 we take 1, 2, 3, 4, and left hand side we take -1, -2, -3, and so on. Okay, so if we take 1 by 2, this is a rational number, you know. Okay, so 1 by 2 basically will lie somewhere here. Okay, so here will be 1 by 2. Okay, so this is how we can represent a rational number on the number line. Okay, so now we'll discuss about real numbers. So basically rational number and irrational number, they together make up real numbers. Okay, so real numbers is denoted by bold R. So we denote real numbers by this letter. So the set of real numbers is basically the union of the set of rational numbers and the set of irrational number. Okay, so if we take together rational number and irrational number, then they will make up real numbers. Okay, so this means every number that exists on the number line. So basically number line means real number line. Okay, so and this means every number that exists on the number line is either a rational numbers or irrational numbers. Okay, so if we take any point on the number line, then that point is either can be expressed as a fraction, that is a rational number, or it is an irrational number that cannot be expressed as a fraction, a over b, where a and b are integers and b not equal to 0. Okay, so now rational number and irrational number, they together making up the entire spectrum of the real numbers. Okay, so now here we'll see how to locate irrational number on the number line. So we already have studied how to locate rational number on the number line. Okay, and locating rational number on the number line is easy process. Okay, easy process. So but locating irrational number on the number line is a difficult process. Okay, so here some step to locate irrational number on the number lines. Okay, so for example, to locate root 2 on the number line. So how can you locate root 2 on the number line? Okay, so first you have to draw a number line and make a point O for 0. Okay, so you have to first draw a line and mark a point O for 0 and another point A for 1. Okay, and now you using in step 2 a compass, draw a perpendicular line at A of length of unit length, that means one unit length. Okay, so first step you have to draw a line, number line. Okay, and mark a point O as 0 and another point A is A for 1, and using compass draw a perpendicular line at A of unit length. And in third step, connect this new point to O and creating right angle triangle with the hypotenuse representing root 2. So here basically the hypotenuse representing root 2 here we get by from Pythagoras theorem. So thanks to the Pythagoras theorem, so now we use a compass to transfer this length back to the number line, making root 2. Okay. So basically, first we take number line. Okay, so we take number line. Suppose here this is our number line. So we mark a point. We mark a point O for 0 and point A for 1. Okay, so this is our 1. And then we have to draw a perpendicular line at A with 1 units. Okay, then 1 units. Okay, so then we connect this new point B with O. Okay, so we connect them B and O, and we get this right angle triangle OAB. So here angle BOA, this is equal to basically 90 degree. Okay, so this here the right, basically here the angle OAB is equal to 90 degree. Okay, so this angle basically 90 degree. So this triangle is a right angle triangle. Okay, this triangle is a right angle triangle, and here the length of OA is basically 1 and the length of AB is also 1. Okay, and now by the Pythagoras theorem, you know, for a right angle triangle, base square plus height square, that is equal to hypotenuse square. Okay, so here basically for this right angle triangle, OA is base and AB is height. Okay, and OB is hypotenuse. Okay, so base square plus height square, this is equal to hypotenuse square. Okay, so by Pythagoras theorem, OB, the length of OB, this is basically equal to square root of length of OA square plus length of AB square. Okay, AB square, and here OA is basically 1, AB is equal to 1, so OB, this is equal to 1 square plus 1 square, this is equal to root 2. Okay, so if we connect the new point B with to O, then it will create a right angle triangle with the hypotenuse that is representing root 2. Okay, actually thanks to the Pythagoras theorem. Okay, then we use a compass to transfer this length back to the number line and marking root 2. Okay, so here we use compass and draw an arc as a center O and radius OB. Okay, so if we draw an arc, this is our right angle triangle. So here we draw an arc, center O, at the center O and radius OB. Okay, so it will touch at some point 1 number line. Okay, and this point basically represent or locate root 2. Okay, this is how we can locate any irrational number on the number line. Okay, so now revisiting irrational numbers. So in class 9th, we were introduced to irrational numbers and many of their properties. Okay, so in our class 9th, there we were introduced to irrational number. There we actually define what are irrational numbers, and there we also discuss many of their properties. Like if we take addition of rational number and irrational number, that then the resulting numbers will give us irrational numbers. Okay, if we take subtraction also, rational number and irrational number, then that will give us irrational number. Okay, for multiplication is also same. Okay, so in class 9 we have already discussed about them. So we studied about their existence and how how the rational numbers and irrational numbers together made up the real numbers. Okay, so we have studied in our class 9th. There we studied how about their existence and how to rationals and irrationals, how the rationals and irrationals together made up the real numbers. Okay, and we even studied how to locate irrational number on the number line. Okay, so now, however, we did not prove that they were irrational number. So there we did not prove basically there we define what are irrational number. Okay, so we define their irrational number as a it cannot be expressed as a fraction, or their decimal expansion is non-terminating and non-repeating. Okay, so there we did not prove that they were irrational number. So in today's lecture, we'll prove that root 2, root 3, root 5, and so on. In general, root p is irrational number. Okay, so where p is a prime number. So one of before proving them are an irrational number, we will see an important theorems. Okay, one of the theorems we use in our proof is the fundamental theorem of arithmetic. Okay, so in this lecture basically we'll discuss an important theorems that is very important to prove root 2, root 3, root 5 is an irrational number. Okay, so let us see. So before we prove that root 2 is irrational number, we need the following theorem. Okay, so we need the following theorem whose proof is based on the fundamental theorem of arithmetic. So student, you have already studied what actually stated by fundamental theorem of arithmetic. So you know, one, every composite number can be written as a product of its prime factors, and this the represent expression this and this way is a unique way. Okay, so in a unique way we can represent them. So before we prove to root 2, root 3, root 5 irrational number, so we need this theorem. So in this theorem basically we first let p be a prime number. Okay, so here we let p be a prime numbers, and if p divides a square, then p divides a, where a is a positive integers. Okay, so here basically p is a prime numbers that we have considered. Okay, and here p divides a square, where a is a positive integer, and then we have to prove p divides also a. Okay, so for proving this theorem we will take help fundamental theorem of arithmetic. Okay, so let us see how to prove it. So here first let the prime factorization of a. Okay, so we let here prime factorization of a. So a, this is equal to p1, p2, p3 dot pn, where p1, p2, p3, pn are primes, not necessarily distinct. Okay, so this is not necessary to being distinct. Okay, so p1, p2, p3, pn, they are prime numbers. Okay, primes. So therefore if we now squaring a, so a square, this is basically equal to p1, p2, p3 dot pn times p1, p2, p3 dot pn. Okay, and this is equal to p1 square times p2 square times p3 square times dot pn square. Okay, so now we are given that p divides a square. Okay, so we have given this p divides a square. So now therefore from the fundamental theorem of arithmetic it follows that p is one of the prime factors of a square. Since p divides a square, so p is one of the prime factors of a square. Okay, so p is one of the prime factors of a square. So however, using the uniqueness part of the fundamental theorem of arithmetic, so we realize that the only prime factors of a square are p1, p2, p3 dot pn. Okay, so P is one of P1, P2, P3, Pn. Okay, so since by uniqueness uniqueness of the part of fundamental theorem of arithmetic, here we realize that the prime factors of a square are actually P1, P2, P3 dot Pn. Okay, so P is on of P1, P2, P3 dot Pn. So now since P A is equal to P1, P2, P3, Pn, and P now from this statement we can conclude P divides A. Okay, so here we can say now if let P is a prime numbers, and if P divides A square, then P also divides A. Okay, so now we are now ready to give a proof that root 2 is irrational numbers. Okay, so the proof is based on a technique that called proof by contradiction. Okay, so in this method, contradiction method, basically actually we assume the statement is true. Okay, then we will come some subsequences, will come some consequences. Okay, and we'll get contradiction, we'll get wrong, we'll get some wrong statement that will give us our assumption is false. Okay, so this technique is discussed in some detail in appendix 1. You can see there. Okay, so here basically we use this method of contradiction method. Okay, so for proving root 2 is an irrational number, here we will use method of contradiction method. Okay, so here we have to show root 2 is irrational number. So first here we let us assume to contrary that root 2 is rational number. Okay, so here we consider its opposite. Here we have to show root 2 is irrational number, but here we assume root 2 is rational number. Okay, so root 2 is rational number, so we can find integers r and s. They are not r and s, and s is not 0. Okay, such that root 2 can be written as r over s. Suppose r and s have a common factor other than 1, then we divide by the common factor, then to get root 2 is equal to a over b, where a and b are co-primes. That means the GCD of a and b is equal to 1. That means a and b have no common factors other than 1. Okay, so root 2 can be written as a over b, where a and b are co-prime. So now b times root 2, this is equal to a. Okay, so b times root 2, this is equal to a. Now if we squaring both sides, then now squaring on both sides and rearranging, then we get 2b square is equal to a square. Okay, so we get 2b square is equal to a square. So therefore here we can say 2 divides a square. Okay, so by the previous theorem, if p is a prime numbers, okay, and if p divides a square, then p also divides a. Okay, here 2 divides a square, and here 2 is a prime number. Okay, so by this theorem it follows that 2 divides also a. Okay, so if 2 divides a, so we can write now a is equal to 2 times some integer c. Okay, so we can write a is equal to 2 times c. Okay, now if we substituting for a, so if we substitute the value of a in this equation, 2b square is equal to a square, then we get 2b square is equal to 4c square. Okay, and it implies b square is equal to 2c square. So this means 2 divides b square. Okay, this means 2 divides b square, and by the previous theorem it follows that 2 divides b. Okay, so 2 divides b. So here we get common factors other than 1 as 2. Okay, so therefore a and b have at least 2 as a common factor. Okay, but in our previous sentence we actually consider A and B are co-prime. That means A and B have no common factors other than 1. But here we get A and B have at least 2 as a common factors. Okay, so but this contradicts the fact that A and B have no common factors other than 1. So this contradiction has arisen because of our incorrect assumptions that root 2 is rational number. Okay, so this is actually our incorrect assumptions. Okay, so by contradiction method we can conclude that root 2 is irrational numbers. Okay, I stop here this lecture. Thank you very much to all of you.